Hi everybody, back to our Cook YouTube again. This series is going to be about our machines that's for junior student at KMTL in our electronics department. Hopefully this YouTube tutoring is going to help you more or less. What I did is I have my lecture note here for 8 pages. So I did the same thing. I upload my materials. You can print it out from the link as follow here: machine underscore series underscore one dot pdf. You can print it out for your reference. Okay, what I'm going to do today is I'm going to start talking about our impedance, just to give you a general idea, and you don't have to memorize anything, and you have get your understanding about what's going on. So what I'm going to do, I'm going to talk about impedance, and then I move along with the voltage, the current when you have your electronic components in the term of resistor, capacitor, and inductors. And then also, you have resistor connect to capacitor in series, and also you have resistor connect to inductor in series. And then we analyze, circuit, just a simple one. So this is going to be a series one of our, about impedance. So let's get it started. To have a right understanding about our impedance, basically it's let me get something here. Okay, sorry. When you're talking about impedance, actually you're talking about a z-plane, and have your unit of ohms, and you can see the plane like this, and I have the vector of z. The length of the vector is going to be the magnitude of z, or the magnitude of your impedance. Since it's the complex number, so you have the real number r, and that's we call resistance, and you have a imaginary part we call reactance. They all have the unit of ohms. And then on the axis, this is the real part, and the top one here is actually imaginary part. And if you do the projection on the x-axis, or the real one, that's going to give you a resistance, and on the y-axis it's going to give you a reactance. And from above here, the z-plane, you can see that you are simply become the magnitude of z, or absolute value of z, multiplied by the cosine of phi. And also our x, or reactance, is simply equal to the magnitude of z multiplied by sine phi. And you also can write the magnitude of z in the term of r and x. This is the very basic one. Just refresh you all. So the magnitude of z equal to square root r squared plus x squared, and then the phase angle of phi equal to arctan the imaginary part divided by the real part. So that's why you have x over r here as called the phase angle. So this is the basic concept, and you can apply this concept to the rest of my lecture notes and the rest of our circuit analysis. So that's what you have. You need looking for magnitude, and you need looking for the phase. Okay, so that's the basic idea. And also you can write your impedance in the term of the magnitude of z, and then the phase angle phi. like this. And the symbol like this one here is represent exponential j phi, and you can expand the term in the term of Euler formula, which is equal to cosine phi plus j sine phi. And if you multiply the magnitude of z into the bracket here, you're going to have two terms, right? The real part here represents resistance, and the imaginary part represents um, reactance, or simply equal to R plus xj. Okay, this is how a complex number works. So in general, when you have R resistance equal to 10 ohms, your impedance simply become the pure real number, 10 ohms. And for the complex number, or the imaginary part, pure imaginary part, you actually get it from capacitor and also inductors, because you know that your impedance of your capacitor equal to 1 over j omega z, when your omega is equal to 2 pi f. And you can write in the term of different term become negative j xc, when xc is your reactant of your capacitor. So that's why I have xc here. And for inductor, z, the impedance of inductor is equal to j omega l, and your omega l you can write in the term of xl, which is reactance of inductor. Now okay, let's analyze each circuit with resistor, with capacitor and inductors. For venue circuit, you have only R only. Let's see if we consider DC voltage source. So I can write V in the term of the absolute value or the magnitude of voltage source, and then the phase angle simply 0. This is the DC voltage source, right? And your Z equal to R, and then you can find the current. Simply divide V by Z, and you can see that the phase of your current is still be the same, right? It doesn't change. So this is what we call the in phase voltage and the current in phase. And later on, you're gonna see here when we're talking about the current leading voltage, or the current phase lacking, or the phase of the voltage. We will discuss soon. And then you see here the complex plane. I can write everything on the same plane, because this is simply complex plane. I can write V, and then Z, and then I, they all have the same phase. So this means the phase becomes 0, or whatever it can be. If you start with V with the phase to be phi, your I still be the same, but your R, the phase is 0, right? Because this is the pure real number. And if I have a Vt in the term of Vm, this is the amplitude multiplied by sine omega t. Your current simply divide V by Z. It still have the same phase, right? Because you have sine omega t. This is what we call the phase. And the magnitude of Z equal to R. This is just for resistor. Now let's move to capacitor. Okay, for capacitor, you know that impedance is become 1 over j omega z, and I start with the DC voltage source. Your z equal to 1 over j omega z, and then you can write in the term of negative j divided by omega z. I just like put j on the denominator, and you can write j in the term of exponential j of negative 90 degree, right? because I want to take the whole term here, negative j, because you know our exponential negative 90 degree j equal to our cosine negative 90 degree plus j sine of the angle negative 90 degree, and cosine 90 degrees simply becomes 0, and sine negative 90 degrees become negative 1. So that's why you end up with, you know, negative j. So this term represents negative j. Now you can see your impedance have the phase what? You can write z in the term of the magnitude of z, which is equal to 1 over omega c, right? The magnitude of impedance of capacitor. And then the phase angle, you need to put negative 90 degree, you know, in there. Okay. So you can see that the phase of your impedance is lagging the phase of V, because it's follow the phase of V. You have the phase of V here, start from V, but your the phase of your impedance of capacitor is like negative 90 degrees, so it's lagging or behind, you know, the phase of the voltage here. That's how you know, end up with, you know, lagging phase, you know, go to 90 degree. Now you're looking for the current, simply equal to V over Z, and then you have Z equal to 1 over j omega Z, and you end up with the I equal to the magnitude of V multiplied by j omega Z, right? Because you move this up to the top. And now you do the same thing. When you're talking about a j, you can represent j by exponential j and 90 degree, right? Because you know that j 90 degree is simply equal to cosine 90 degree plus j sine 90 degree. This give you 0, and this is give you 1. So you end up with j, right? That's why you have current equal to the magnitude of V multiplied by omega c, and then the phase is 90 degrees. So it means it's leading the phase of the voltage 90 degree. So that's why we said I have it here as the leading V 90 degree. But your impedance of your capacitor is lagging the phase by 90 degree. Okay, so this is how your capacitor works. Well, if you understand the basic idea, let's move to our inductor here. You do the same thing. Analyze DC voltage source. Your ZL impedance of your inductor is equal to j omega L, and then you can write j in the term of exponential j 90 degree. And then that's why you have the leading phase compared to the voltage is 90 degree. This is for impedance of the inductor. But you take a look at the impedance of the capacitor, you can see that is the lagging or behind, you know, the phase of the voltage by 90 degree. So that's what different. Just work out perfectly. For the current, you divide the voltage by Z, and then you know, you lift that up, so you get your negative J. You can write negative J in the term of exponential J negative 90 degree, or simply you have the phase, you end up with the phase negative 90 degrees. So that's why your current is have the phase lagging compared to the phase of your voltage, while your impedance of the inductor is leading, you know, the phase of the voltage by 90 degree. Okay, so that's the basic concept. And if you want to take a look at the plot, oops, you can see you start with the voltage here. This is the complex plane. So for inductor, your current is lagging, you know, the phase of the voltage by 90 degree, but your impedance of your load is going to leading the voltage by 90 degree. Okay, and you can do the same thing when you have the voltage source to be Vm. This is amplitude multiplied by sine omega t. You have the current here equal to V over ZL, and you simply write negative j in the term of exponential j negative 90 degree, or the phase is become negative 90 degrees, so it's follow the phase of the voltage. That's why I have the lagging current here. Next, let's take a look at the we already take a look at the R only, and then C only, and then L only. Now take a look at the series circuit with R and L and R and C circuit. So let's start with the RC circuit here in series. Still, doing on the DC voltage source. Well, the simple way to analyze the circuit, just follow my step like this. You're looking for the current is equal to voltage divided by impedance. Now your impedance, total impedance of the circuit is become R plus 1 over j omega c, right? This is your total, impedance of your circuit. So I write this one in the term of the magnitude of Z multiplied the phase anchor of impedance, where the magnitude of Z equal to square root R square plus 1 over omega c square, right? And your phase anchor simply divide imaginary part, which is 1 over omega c, right, by the real part, which is R. The reason I have negative here because I change this one 1 over j omega c to be negative j over omega c. So you end up with the phase anchor to be negative number here. And for your current, simply equal to V over Z. So the phase of the current has become a positive phi. And if you draw the diagram here, you start with V, you have Z with the phase become negative number here, right? Because you have a negative J over omega C. But your current, the phase, is going to be a positive number. Okay, it depends what is the number right here. It can be leading the voltage, I mean current, or it can be lagging the voltage of the current. It depends on phi. Now analyze the AC circuit here. AC supply voltage. You have Vt equal to Vm sine omega t I. You do the same thing. You lift it up. So for when you have capacitor, you see that it's going to lead the voltage by phi, while the phase of your impedance is gonna lagging the phase of voltage by negative phi. Okay, you probably be able to analyze this one by yourself. Now let's move to RL circuit in series. When the total impedance equal to R plus j omega L, and then equal to the magnitude and the phase anchor. So again, you can find the magnitude of your impedance equal to square root R square plus omega L square. And then your phase anchor here is going to be your imaginary part, which is omega L, divided by the real part, which is R. So you end up with the positive number of your phi. So that's why it's leading the phase of voltage. The same thing for the current. You divide V by Z, so the phase, turn out to be your negative or phi. So it's lagging V, by negative phi. And you can draw the diagram like this. You start with V. Your Z is the leading rate of the voltage because you have the positive phi here, and for I, it's going to the opposite direction. It means is moving in the direction of clockwise. When Z is moving to the direction of counterclockwise. Now let's move to the topic of power and power factor here. Well, you have basic idea already. power is simply become P equal to I multiplied by V, right? And that's mean you have the voltage source here and you have the load here, and you want to transfer your power, from the source to the load, and you want to calculate, the power, at the load N here. P equal to IV, and then in general, you just simply multiply V by I. So if I have V become Vm sine omega t, and I is Im sine omega t plus and minus phi, amplitude multiplied by sine omega t plus and minus phi. The reason I have plus and minus theta here, when theta is the phase difference between the voltage and the current, it can be leading or can be lagging compared to the phase voltage of the voltage source. So that's why I wrote this out in general form, plus and minus. Now to analyze, the equation, I use the property of sine A multiplied by sine B equal to 1 over 2 cosine A minus B minus cosine A plus B, or cosine A plus B equal to sine A multiplied by sine B minus cosine A. Sorry, this have to be cosine, right? My mistake again. But for sine A plus B, you have a sine A cosine B plus cosine A sine B, but we're going to use this one here. So what I have here, I have this is A, right? I have this is one B, right? I want to use this property because in the term of sine A multiplied by sine B, this is sine multiplied by sine, right? So I can write this term in right here, 1 over 2 cosine A minus B, this is my B, and then minus cosine A plus B, right? Now you take a look at this one. Omega is cancelled out, omega t. This is plus and minus theta, and this is become cosine 2 omega t, right? Plus and minus theta. You take a look at this one here, cosine plus and minus theta. It doesn't matter, they're all equal, right? Actually, it's the what? Cosine theta is the even function, right? Because you have a negative, sine positive sine. Cosine plus theta is going to be equal to cosine negative theta. This is what we call even function. So that's why for the P positive, I have P here equal to 1 over 2 multiplied by Vm Im, the amplitude of the voltage and the amplitude of the current, and then multiplied by cosine theta. Theta is the phase difference between the voltage and the current. Okay, so that's how you find the average power. Well, now what we have, new term here. You have a cosine theta here. They define cosine theta as the power factor. Take a look. When you have theta is the phase difference between V and I. Well, for the case 1, I have only R, right? So I don't have the phase difference between voltage and the current. So voltage and the current are in phase, or theta equal to 0. So my power factor actually is equal to 1. So that means if they are in phase, I mean the current and the voltage, so you have the power factor become 1. But in the case of you have a C and you have L, when they have a leading and lagging in the term of the phase of the current and the phase of the voltage, you have a pure reactance or only imaginary part. You have the phase difference between become a positive 90 degree or negative 90 degree, and thus give you the power factor becomes 0. for both cases. Okay, so you make conclusion again for capacitor. You reconsider again. I leading V. So when you multiply I and V, so you have leading power factor. For inductor, I lagging V. So that means you end up with a lagging power factor. Okay, so this is the average power, and also you have the definition of power factor. Next, apparent power. Well, I want to write, power in the term of complex number. In this case, you're going to have the real part and imaginary part. So the real part actually is come from a resistor. For imaginary part, is actually come from capacitor and inductors. This give you imaginary part. So to get a better picture, let's take a look at it as plane here. You have vector S here. You have the real part. You have the imaginary part. So S is equal to P plus QI. This is your P and this is your Q. And you can find P in the term of S simply the magnitude of S multiplied by cosine theta, right? And for your Q, simply equal to the magnitude of S multiplied by sine theta, right? Also, S equal to V multiplied by I complex conjugate. What does it mean? What does this mean? Complex conjugate is mean if I equal to 2 plus 3j, your complex conjugate simply change the sign of imaginary part to be opposite. So I change this one to be negative 3. This is what we call complex conjugate of I. So if you start with I, V with the phase angle to be alpha and I with the phase angle to be beta, V still be the same, S equal to V multiplied by I complex conjugate. So I need to change the phase of your current to be a negative beta. And you add up the phase together, so you have alpha minus beta. So that's why I have S equal to VI. You expand this term here. And then cosine alpha minus beta plus this term and then multiply by sine alpha minus beta multiplied by J. As I mentioned at the beginning here, P equal to S equal to the real part plus imaginary part. So you know that this is the real part only, so it's become P, the average power. And then the second term we have J. This is imaginary part, so that's give you Q, right? This is imaginary apparent power. This is the real apparent power. So as I mentioned earlier, alpha is the phase of voltage, beta is the phase of current. So you take a look at alpha minus beta. If alpha minus beta, this gives you a positive number, right? So that's what we call V leading I. But if alpha less than beta, I is going to leading V. Okay. So alpha minus beta equal to phi. And also keep in mind S equal to P plus QJ. Okay, so that's how we define apparent power, simply equal to S plus P plus QJ, the real part and imaginary part. And you can take a look at the S plane here to get better picture. Well, for the single phase, alpha minus beta equal to 0. This means you have no phase difference, because alpha is the phase of voltage, beta is the phase of the current. So take a look at this one here. You have, this is your P, right? Or simply you can just take a look at the diagram here. Your P equal to magnitude of S multiplied by cosine theta here. And the magnitude of S is simply the magnitude of voltage multiplied by the magnitude of the current. And for you, Q is equal to the magnitude of S multiplied by sine theta, right? Here. So when you're talking about a single phase, the phase difference is 0. So you plug in theta equal to 0. This is give you 1. For sine 0, this is give you 0. So it's give Q becomes 0 watt. And now you are looking for a power factor. You take a look at the diagram here. How do you find cosine theta? So cosine theta simply become P divided by the magnitude of S, right? That's why I have here. What is your P? P is P. S is what? The magnitude of S is magnitude of the voltage multiplied by the magnitude of the current. So that's why you have cosine theta equal to P over S. Okay, so you probably not get confused, if you take a look at the diagram here. What about R over Z? Well, you take a look at the Z plane here. As I defined, you have the real part and imaginary part. The real part is resistance, right? The imaginary part is what? Reactance, right? X. And you want to find cosine theta, simply divide R by the magnitude of Z, or the magnitude of your impedance. So that's why I have R over Z here. Okay, I think this way is better, because some students still confused how how to get these equations here. So this is the single phase. So the phase difference, that means the phase of the voltage and the phase of the current difference is become a 0. Okay, next. I also be able to write apparent power, or the magnitude of the power, in the term of S equal to V multiplied by I, or I squared multiplied by Z impedance, or V squared over Z. The same as you work out on this equation before. So when you're talking about a magnitude, you simply put the absolute sign to V multiplied by I complex conjugate. Now you take a look at the real or average power. As I told you before, just take a look at the S plane, right? This is the magnitude of S. So the real power, the real part here is give you a power. So that's what we call real power. And you get it from resistor. And from this case, you have a P equal to S multiplied by cosine theta. So that's why you have P equal to S. This is S, right? The magnitude of the voltage multiplied by the magnitude of the current, and then you multiply by cosine theta. And that's equal I square R equal to V square over R, because it's come from R only. This is the real part. Or you can write P in the term of the real part of your S, or the real part of your V multiplied by I complex conjugate. So that's true, right? Because you have S equal to what? P plus what? Q J. I mentioned earlier, right? This is V multiplied by I complex conjugate. You end up with P plus QI. So you want to take the real power. So you take the real part. So that's why it becomes P. And the same thing, if you understand this concept, you can find reactive power. So this has come from imaginary part of your S. I pick up Q here, so that's why I put Q equal to imaginary part of your S. And your S is the V multiplied by I complex conjugate. And for Q, I have this equation because you take a look at the S plane. You have Q here, right? become the magnitude of S multiplied by sine theta, and the magnitude of your S equal to magnitude of V multiplied by magnitude of I, or equal to Ix squared, or equal to V squared X over X, because it comes from reactance. And for P is the real power is come from R only. Okay, so this diagram again gives you better idea to analyze your circuit, RLC circuit. What about here? Well, when the case of inductor, I is lacking V, right? The phase of I is follower the phase of voltage. So that's why I have I here. It's follow the phase of the voltage, because you take a look in the direction of counterclockwise. So if you have I equal to 2 minus J, this is just for to get better picture. So my I complex conjugate, because you are looking for V multiplied by I complex conjugate, right? My I complex conjugate is become 2 plus J. So that's why I have I complex conjugate up there. And when you multiply V to I complex conjugate, you end up with the S plane like this. You can find your Q equal to the magnitude of S multiplied by sine theta, and you can find P equal to the magnitude of S multiplied by cosine theta, and the magnitude of your S simply become square root P square plus Q square, right? This is like a vector. And the same thing as for capacitor, you have current leading voltage. This is the current leading voltage, right? And you're looking for I complex conjugate. I have 2 minus J. And you do the same thing, to find the real power and the reactive power. Well, take a look at an example here. You have voltage in the term of RMS is 200 volt, and the current is 5 mRMS. And our power factor is given equal to 0.75 lacking. Ask you to calculate for the power, the apparent power, the real power, the reactant power, the impedance Z, resistance R, and the reactance X. Well, you start from power factor equal to 0.75, that's given, which is equal to cosine theta, and you can find theta equal to arc cosine 0.75 or 41.41 degree. Now the magnitude of your S is what? Because if you can find the magnitude of your S, you can find P, you can find Q, right? Because P is the real part of S, and P equal to the magnitude of S multiplied by cosine theta, and your Q is the reactive power equal to the magnitude of S multiplied by sine theta. We already know cosine theta because it's given, right? You can find the magnitude of S, you can find Q and P. Well, the magnitude of S simply equal to V, the magnitude of V multiplied by the magnitude of I, which is equal to 200 volt multiplied by 5 amp. That's give you 1000 watts VA, right? So your P is equal to the magnitude of S multiplied by cosine theta. So you multiply by 1000 to the power factor, which is 0.75. This gives you 750 watts. For your Q is equal to what? The magnitude of your S multiplied by sine theta, which is the 1000 multiplied by sine theta, which is square root 1 minus the cosine square, right? This is my cosine. So I end up with the Q equal to 661 VAR. Next, Z. Well, Z, the impedance equal to voltage divided by current. So it's become 200 over 5 amps, which is 40 ohms. Now take a look at this one, the Z plane. You probably, have no difficult time to find reactance and resistance, because your resistance equal to the magnitude of Z cosine theta, right? And your reactance is equal to the magnitude of Z multiplied by sine theta. So you R equal to magnitude of Z cosine theta. You already have the magnitude of Z, which is 40 ohms, and cosine theta is the power factor is given, right? 0.75. So it's give you resistance equal to 30 ohms. And your what? Reactance is equal to the magnitude of Z multiplied by sine theta, which is the 40 ohms multiplied by square root 1 minus cosine square. So that's give you 26.4 ohms, right? Okay, so that's our the um, talking about our impedance in the term of R, L, C. This is a series ones, and I will move, to series 2. So I'll see you next YouTube. Thanks.